Hi, I'm Hiroki Usuba from Yahoo Japan Research. Today, I will talk about predicting touch accuracy for rectangular targets by using one-dimensional task results. A success rate for touch pointing is the probability that touch points fall within a target. This rate is predicted by modeling the endpoint distribution. High success rate means that users accurately perform the operations. The touchpoint distribution becomes a dual Gaussian distribution. And the dual Gaussian distribution consists of two Gaussian distributions. On the basis of the dual Gaussian distribution, the success rate can be calculated by the double integration. Here, D is a target region. In rectangular targets, the region consists of the target width and height. Sigma x and y are the variance of the touch points. Especially in the 1D environment, the success rate can be predicted by the Gaussian error function. Comparing the 2D and 1D success rate models, because most of the dual components are rectangular, the 2D model is more practical than the 1D model. However, the 2D task is more difficult. So, the 2D task is time-consuming. For example, we wish to set the experimental condition for width and for height in the 1D task. We can set 10 repetitions. In the 2D task, if we can only use the same amount of time as the 1D task, we may set only at most 5 repetitions. However, for accurate success rate prediction, many participants and repetitions are desirable. Generally, double integral can be broken to two independent integrals. So, the 2D success rate model can be expressed as functions of x and y. And the function of x and y can be replaced by the 1D models. So, the 2D success rate model can be expressed by multiplying the 1D models. On the basis of the transformation, we hypothesize that the 2D success rate can be predicted by the 1D task results. We will explain our method. First, we conduct two tasks, 1D vertical and horizontal bar tasks. Thereby, we obtain parameters sigma x and sigma y from the 1D task results. And we obtain the success rate for the two rectangular targets. Our contribution is as shown on the slide. First, we show that the dual Gaussian model can be applied to rectangular targets. A previous study showed that the model can be applied to only circular targets. Second, our method allows to predict the success rates for more practical situations and few experimental conditions. In short, our method can predict the success rate for the 2D targets from the 1D task results. Experimenters have only to conduct the 1D tasks with for width and for height instead of the 2D task. Thereby, our method allows to decrease the experimental time and thus save costs for participants. In this study, we verify our methods through laboratory-based and crowdsourced experiments. First, we conducted a laboratory-based experiment. 12 participants joined the experiment. The participants conducted 3 tapping tasks, horizontal bar, vertical bar, and rectangular target tasks. In the tasks, the target appeared in random positions with various sizes. The participants repeated the experimental conditions 30 times for each task. A tablet displaying in the experimental task was on a flat table, and the participants tapped the targets with their index finger. We checked the success rate for the 2D targets by using the 2D task results. A previous study found a linear relationship between the sigma and width. We also found that the relationship showed the high fitness. We found that the high and width had a main effect for the success rates, but did not find an interaction effect for the high and width. So, the high and width independently affected the success rate. The mean absolute error was 2.39. The mean absolute error is the average of the difference between the predicted and observed success rates. In summary, we succeeded to predict the success rates for the rectangular targets by using the 2D task results. Next, we checked the success rate for the 2D targets by using 1D task results. Like using the 2D task results, we found that the linear relationship showed the high fitness. The mean absolute error was 4.04. In experiment 1, using the 2D task results, could predict the success rate for the 2D targets. Using the 1D task results showed somewhat higher mean absolute error than using the 2D task results, but the accuracy was not low. So, the success rates for the 2D rectangular targets can be predicted by using the 2D and 1D task results. Next, we conducted a crowdsourced experiment. 397 crowd workers joined the experiment. The workers conducted the same 3 tasks as in experiment 1. We instructed the workers to hold the smartphone in their non-dominant hand and to tap the targets with the index finger of their dominant hand. The workers repeated the experimental conditions 40 times. Our experimental system identified the smartphone model and drew the same size targets across different devices based on the PPIs. First, we checked the success rate for the 2D targets by using the 2D task results. We found that the linear relationship showed the high fitness, and the mean absolute error was 3.09. Next, we checked the success rate for the 2D targets by using the 1D task results. We found that the linear relationship showed the high fitness, and the mean absolute error was 2.15. In summary, in the crowdsourced experiment, we found that the dual Gaussian model could predict the success rate for the 2D targets by using the 2D task results. And by using the 1D task results, unlike experiment 1, the accuracy was improved. So, in the crowdsourced data, using the 1D task results improved the prediction accuracy. Again, in experiment 1, which is laboratory based, using the 2D task results improved the prediction accuracy. But using the 1D task results could sufficiently predict the success rates. And in experiment 2, which is crowdsourced, the prediction accuracy by using the 1D task results was better than using the 2D task results. Comparing the linear regressions between the sigma x and width in 2 experiments, the R squared in experiment 2 was higher than in experiment 1. Increasing the number of participants increases prediction accuracy. Because experiment 2 had more participants, than experiment 1, the R squared in experiment 2 was improved. On the basis of the experimental results, we recommend what this slide says. If many participants join an experiment, for example, a crowdsourced experiment, researchers should conduct the 1D task for the success rates for the 2D targets. Because the 1D task saves time compared to the 2D task, the researchers can increase experimental conditions or repetitions. They can save costs for participants or experimental time, or they can conduct additional tasks. On the other hand, if few participants join an experiment, for example, a laboratory-based experiment, the researchers conduct the 2D task. But if the researchers wish to save cost or conduct additional tasks, using the 1D task results may be good. Because using the 1D task results with few participants' data can sufficiently predict the success rates. Our claim is not that researchers should always use our methods, but that they can use properly our methods depending on situations. Proper use of our methods can contribute to researchers, experimenters, and participants. This slide is a summary of our study. Thank you for listening.